Welcome back, everyone. So I want to do a recap of last week's stream, and but maybe we start with a recap of the project as a whole. So we've been trying to find some way of going from a genome, looking for genes that are overly short, and trying to quantify if there's an excess of these overly short genes, because we think that that can be an indicator of low genome quality, in particular of having too many, short indels that break up genes, right? So we've been doing this through simulation, and we've been looking at a handful of genomes, sort of E. coli, Bacillus cereus, those kind of, stars of microbiology, and we have defined this score, probably not the final version, but we defined this score which takes a gene, classifies it to a KO, and then uses the GMGC, so the Global Microbial Gene Catalog, as a calibration set to go from the actual size. If you have a genome and size, 300 amino acids, what does that mean? Is that a gene that's too long or too short? And so we've been using the GMGC to say, okay, we classify it to a KO, and then we see what's the background distribution of gene sizes for that KO. And so if a gene has size 300 is in a KO where the average size is 300, then that's where we expect it. If the average size is 600, then it's half the size. And then we go a step further, and we can also use the standard deviation, to transform it into a Z-score or a Z-score for the Americans, where we can now say, this has a Z-score of -5, so it's extremely short, much shorter than we expected, or it has a Z-score of 0, meaning it's exactly where we expected. Right? And so this last week, what we did is we switched. So we started to, first of all, we did a little bit of cleanup of the code that was written from before, and then we started to expand our data set. So I'm going to share my screen now. We started to expand our data set. So here in our download data file, download data. So this, I think we had this before, download E. coli, we had top few. So we added a couple more, but even more importantly, we started to download all of the representative genomes from Progenome 2. So here, if you don't know Progenomes 2, or Progenomes 3, sorry. So if you don't know, Progenomes is this database of genomes and you can download the representative set. That means you get one genome for each single species, so that we have just one genome per species, and that's going to be actually, just double check, that's going to be 40,000 species, right? So we downloaded that, and then we also, just to be sure, we're sort of finding this, we went to Spire, and so Spire is a database of metagenome assembled genomes, and we also downloaded the mags from this study. Happens to be a study I did several years ago. So we just downloaded mags, so we have these to work with. So we wrote this code during the session, and then, oh no, we didn't finish, oops, sorry, but we ran it, and now everything's done. So everything's ready for us to work on this tomorrow. Right, and then we also worked to expand the data set we're working with. So the first step was actually very trivial. So we just added these couple of extra species here. But what was nice is that this also triggered an error here, because whereas previously every genome was a single contig genome, now some of these are multi-contig genomes, and so we have to adapt the code a little bit. And so what we did, we added this padding. Right. So having done this, again, this did not run during the stream, but afterwards I was able to just leave it running, ran perfectly, finished, and we got the result. So this is the result we get, where we have here, this is as before, so this is our sum of Z scores below -4. Again, this might not be the final version of the score that we use, but it seems to work quite well so far. So the dashed lines represent what we get for genomes without any simulated mutations. So this is what we would use to calibrate the score. And so interestingly, E. coli still gets the lowest score. We'll see what happens when we run it on everything. And then every other genome, it starts to go down quite quickly. Prevotella maybe slightly less quickly for some reason. And as you can see, this is somewhat promising, at least when we get this regime here with 1,000 mutations. Most of these are well below what we get for the unmutated versions. Again, we will know much more later in the week once we've run much larger data sets. And so that's what we'll be doing tomorrow. So tomorrow we'll be doing two things. So first of all, consolidating what we have, cleaning up the code. The code is a little bit slow, and it saves a lot of intermediate files, which I think was perfectly fine and acceptable when we were working with a handful of genomes. Maybe a little bit annoying at times, but still within the acceptable range. It's not going to be acceptable when we multiply everything by by 1,000, when we're going from 8 genomes, or 10,000, because we're going from 8 genomes to 40,000. So we're going to have to clean up the intermediate code, pre-compute some things, and then but then we'll potentially be able to run this on at least a large subset of all of the representative genomes. Maybe we don't need the 40,000 this week, maybe, but if we get a couple hundred, that's already well represented, right? So that's what we'll do tomorrow. So see you tomorrow. In the meanwhile, everything is posted on the GitHub. I'll post this on the mailing list as well. So please follow us there. There's a Discord, and please do subscribe to the channel. And I will talk to you soon.